Alright, what's up YouTube? This is G-Man coming at you. So, I'm back with part number 9. And, okay, first thing I want to show you, we're continuing off right where I left off in the last video. So, first thing I want to show you, I looked up this nifty little clip. This is from Rob Skiba's video, Flat Earth and Atmospheric Magnification, short version. And if I ever get around to it, which I probably should get around to it as soon as possible, I will add the link to this video at the bottom of this video. Okay, so you have to see this. Watch this.
Magnification. So in this scenario, you have more magnification, and in this one you have less. And for this one, I decided to put the Toronto skyline into my little box here. Let's try it again. Okay, we're all the way up against the glass. Now let's zoom across the lake. And wow, look at that. The lower portions start to disappear. Now let's zoom back in, get a little closer to the one that Captain Baltard was talking about here. And wow, look at this. Here's his image on the right, and here's my image on the left. Missing the lower portions of the city had nothing to do with curvature whatsoever. Thanks so much for watching. I hope you enjoyed this video presentation. If you did,
Alright, so Mr. Sungenis, how did you miss that part of the video? How? Okay, we're going to continue because the 1/3 of the building that was underneath the horizon that you call looming was just shown in that video exactly how the 1/3 of the building can be under the horizon under a completely flat Earth. Here we go.
We only see about 2/3 of it, and so we would ask the flat earthers, so where's the other third? If we all understand,
where's the other third? I just showed you in the video just 2 seconds ago. Okay,
that some type of refraction, and we'll call it looming, is bringing up part of the building. Where's the other third of the building? Obviously, it has to be below the horizon. And no magnification, no binoculars, no telescope is going to be able to bring up that third of the building because it is below the horizon, you see. And this was one of Rob Skiba's arguments. He says, well, if you magnify the building, it'll bring it up close and you'll be able to see the building. And we'll say, yeah, you can see the building, but you can't see the whole building. And that's because at 60 miles away, or 46 miles away, where Skiba was in this boat, you're not going to be able to see the whole Willis Tower. So
incorrect, Mr. Sungenis. Incorrect. I just showed how the building, the 1/3 of the building, could sink underneath a completely flat surface by use of magnification. Rob Skiba did the experiment in his video. Very simple experiment to perform. All you need is 0 elevation. You just got to be right there on the ground. You can do it on a flat table surface. And what more could you ask for? Okay, let's move on.
So, this is how technical these things can become, and you have to be educated in atmospheric conditions and how cameras take pictures and all these kinds of things before you even begin to answer the flat Earth argument. So this is why the flat Earth movement has become so big, because there's all these technical points that you are faced with that you have to address. And so it's a big battle back and forth of who knows the science better, as you will see on YouTube if you venture into this rabbit hole. As far as taking pictures, we have pictures taken from, hundreds of miles up of the Earth. And many of these pictures are taken with a wide-angle lens. Now, what a wide-angle lens will do is, if the Earth is put on the outskirts of the lens, on the outer dimensions of the lens, it's going to curve the Earth because that's the way the lens is formed. And so a lot of people were using wide-angle lens shots of the Earth as proof that the Earth was curved. And you can't do that because a wide-angle lens will distort it. And the only time that the wide-angle lens will give you an accurate picture is if the edge of the object goes right across the middle of the wide-angle lens, you see. And so now we have to confine the debate to, well, where is the edge in the wide-angle lens? If it's in the middle, do we see any curvature, even when it's in the middle? And it's very hard to see any curvature because what they call the FOV, the field of vision of a lens, is so limited that you're not going to be able to see the curvature in a lens, even if that edge of the edge of the Earth goes right over the center of the lens.
Okay. Flat earthers agree that you have to get, I think it's 100 miles up before you can even begin to see the curvature. We agree about that, okay? Well, I mean, we would actually argue that you can't see, there's no curvature to be seen, even if you go 100 miles up, okay? Because everything that we send up, weather balloons and rockets, as high as it can go, you see zero curvature. So, if there is any curvature to be seen, we have to rely on NASA. And guess what? We don't trust NASA. NASA's lying to us. So, these videos that show us the curvature that you look at from NASA, you know, they've all got the fisheye lenses. You know, they actually, you know, don't represent reality in many cases. Okay, they're hiding the fact that, you know, they're above a curveless Earth, Earth without a curve, and there is no curve, so they're hiding that fact. So the thing that's important here, however, is the horizon drop, the drop in horizon. So you got the horizon that rises to eye level, and it should on a plane, on a plane, not an airplane, but a plane, okay? Or you can be riding in an airplane, and the horizon will rise to eye level, and you can go up in a weather balloon up to 24 miles. The horizon will rise to eye level, okay? But past that weather balloon, you've got to send up a rocket, which can go higher, and the horizon will rise to eye level. At what point does it no longer rise to eye level? Because boats go over the curvature, according to science, everything that I've learned my whole life. Boats go over the curvature at 5 miles, 3 to 5 miles, and so you see the boat go over the curvature, and so that means that the horizon should drop away from eye level. That you take off from the Earth, and the horizon over here, it shouldn't rise to eye level. It should drop eventually. Okay, so the horizon should never rise to eye level once you get past a certain point. It should completely stop. I don't know what that height is. Okay, they've got a computer simulation that'll tell you that height. It might be a good idea for me to show you in the next video. I need to look that up myself. Okay, but anyways, but guess what? This is good stuff. You know, it's getting me to look this stuff up. Okay, so you got the horizon. That's what's in question. Horizon should not rise to eye level. If a boat can go over the curve in 3 to 5 miles, you should get to a point where the horizon is down here, and you've got to look down to see the horizon. Okay, but so far, the only way that you can, the only thing that makes the horizon drop below your eye level is NASA. NASA is the only ones that's telling us that the horizon drops below eye level. They're the only ones that's telling us that the Earth has a curve. So you've got to defer to them. But hey, we don't trust NASA. We don't trust NASA. So anyways, this video is about 10 minutes, and we're gonna need to start up a new video. Okay, G-Man out.